Model-based testing is a species of automated testing, which is a somewhat different approach than unit testing, which is so well supported by many tools. Basically, the idea the main difference in unit testing, the test engineer or the developer has to code each test case. They code what happens in the test case, and they code an assertion that checks that the test passed or failed. As a result of that, the amount of testing is proportional to programming effort. So the thoroughness of the testing, the coverage of the testing is also proportional to programming effort, and that's the limitation. In automated testing methods, including model-based testing, you have to invest a certain amount of programming effort to get the test situation set up. But after that, you can generate essentially infinite tests with no additional effort. So that the amount of test after this initial investment of effort, there is no additional effort needed to get additional test coverage or additional thoroughness of testing. So that's the advantage of automated testing techniques, including Python. So what kind of problem does model-based testing solve? Like, actually, unit testing is quite adequate for many kinds of systems. The main thing is that the main problem that model-based testing was invented to solve was when you must test behavior rather than just results. By behavior, I mean some ongoing sequence of actions where the correctness of the correctness of the system isn't just delivering a particular result. It's the entire behavior. And so, in order to generally to test behavior requires very thorough testing and a lot more test runs than functional behavior, because there's generally a lot of different interleavings that have to be checked and a lot of non-determinism in the system. And so another way to look at that is unit testing is really more oriented towards functional systems where, you know, the same operation with the same input should produce the same results. That's what we mean by functional behavior. But many systems do not have functional behavior. That is, they have state, or they have memory, or they have some stored information that accumulates as the behavior proceeds, so that later in the behavior, the same operation with the same inputs does not always result in the same results, and it is, in fact, isn't supposed to. And so model-based testing provides a way to account for that, this sort of state-dependent behavior. So examples of systems that exhibit this state-dependent behavior are communications protocols, web applications, control systems, user interfaces. So it's not that rare. So, okay, I've been telling you we need to test behavior, or model-based testing tests behavior. So what do I actually mean by behavior? That is, how do we represent behavior for the purposes of model-based testing? Well, we represent behavior by things we call traces, which are samples they're samples of behavior which are represented by things that look like sequences of function calls. That is, a trace consists of a sequence of actions. Each action has a name. That's like the name of the function. And an action may have parameters or arguments that look like the arguments of a function call. Behavior is represented by these traces. Now, it so happens that any system can be characterized or specified by the collection of traces it is allowed to produce. And essentially, the model that's used in model-based testing is a program which either generates traces. Generating traces is creating test cases. Or it's an oracle that can check traces. That is, as a generator, the model can generate any trace which is allowed, but never generates a trace which is not allowed. And as an oracle, the model will accept any trace that is allowed and will reject any trace that is not allowed. Now, in general, there are an infinite number of traces, both infinite allowed traces and infinite forbidden traces. So we need a compact way to represent the model that can accommodate this infinite number of traces. So here, what I mean by traces, it's useful to have some examples. These are traces generated by, these are traces from something called the alternating bit protocol. The alternating bit protocol is a protocol for dealing with lossy or noisy communications channels. Basically, it's just this. You keep sending the same message. The sender keeps sending the same message labeled by a bit, either 1 or 0, until the receiver acknowledges with that same bit. And then the sender keeps sending the next message labeled by the opposite bit. So you flip the bit and every time you send a new message. So basically, this protocol defines an infinite number of allowed traces, and also there are an infinite number of forbidden traces. And I won't explicate these here, but I'll just sort of point to them. So recall, we want to have a compact way to represent this huge family of acceptable and unacceptable traces. Well, PyModel provides a couple of ways to do this. In fact, there are a couple of kinds of models that are provided, that are supported by PyModel. And the first one I'm going to discuss, although not the most commonly used for modeling, is a finite state machine. So a finite state machine is a kind of model you can use to represent finite systems. And by finite systems, I just mean there's a finite number of actions. That is, there's a finite number of functions and there's a finite number of values for the arguments. Therefore, there is a finite number of things the system can do. And you can represent such systems with finite state machines, which are often represented by tables or by diagrams like this. And the notable thing about this is every allowed trace can be derived by just tracing paths around the finite state machine. Every allowed trace. So even this very small, simple finite state machine can generate an infinite number of traces. And likewise, you will never, by traversing around this thing, generate one of the forbidden traces. So here's how we can represent a finite state machine in PyModel, or in Python. This is how PyModel does it. You simply represent the finite state machine by the graph of the finite state machine. That is, it is a tuple of tuples, where each tuple represents one edge in the finite state machine. It's a triple where the first element is the start node, the last element is the end node, and the middle element is the edge label. So actually, this graph here was generated by one of the programs in the PyModel testing suite, which is PyModel Graphics. So now I'll tell you how testing works. The PyModel tester generates traces from a model. Each trace describes a test run, including the expected test results. So in this case, PMT simply traverses the finite state machine and can generate a sample trace. For example, here I ask for a trace that has 10 actions in it, and this is what we get. Now, to execute these tests, there's one additional thing you need to know, or one other thing that PyModel needs to know. There's a distinction between controllable actions. Controllable actions correspond to functions in the implementation that the tester can call. And then there are observable actions, which correspond to actions that the tester cannot call but can only observe. They're essentially the results or the outputs of the system. And so actually which is the controllable and which is the observable depends on where you are in the system. So for example, if you're testing the sender and your test harness is connected to the sender, then in this example, the sends are the controllable actions and the acts are the observable actions. On the other hand, if we were testing the receiver and we had our test harness connected to the receiver, then the sends would be the observable actions and the acts would be the controllable actions. So that's how trace generation turns into test case generation. Now there's a couple of ways that testing can be done. One is what we call offline testing, where basically the PMT program generates some sample traces and you save them, and later you play them through the test runner, which again is PMT, it turns out. And those constitute the tests that you check. So that workflow is actually a lot like unit testing, except that PMT itself generates the test cases after you write the model. So, but the workflow, other than that, the workflow is like unit testing in that you have these files sitting around, which are the tests, which you can run over and over. There's another kind of testing called on-the-fly testing, where you actually generate and check the test for the first time as the test case executes. And on-the-fly testing is used. On-the-fly testing is especially useful when there's non-determinism in the system, because the tester can actually respond to the non-deterministic behavior of the system on the fly as the system is executing. So that's quite a different style of testing. Now, I'm going to go back to models. Remember, we discussed finite state machines. That's one way of building a model. Another way, but it's only for finite systems. That is, systems where all the arguments of the actions are drawn from a finite set of values. Like in that example, it was just a Boolean value. Well, actually, that's rather unusual. The more usual way to define a system is to write a model that we call a model program, which is a Python program that's written according to this following format. It consists of state variables, action functions, and enabling conditions. So here I'm going to take another example, which is just a stack. Please forgive these very simple examples, but here the model program just fits on one slide, which is why I chose this example. So you have the state, which is the information stored in the model, which for a stack I'm just using a Python list. Then you have the action, then you have two actions, push and pop. The push action takes one argument, and you can see that it actually just pushes the element onto the front of, inserts the element on the front of the list. The other action is pop, which simply removes the element from the beginning of the list and returns it. So there's nothing unfamiliar there. But the one wrinkle that's new that makes this a model that PyModel can use is there are enabling conditions. Enabling conditions are how you express the ordering constraints in the model. So the ordering constraint in the stack is, well, push is always enabled. So it's ordering, it's basically the enabling condition is a Boolean function of the arguments and the state variables, which returns true for all states and all combinations of action arguments where the action is allowed to occur. So push is always enabled. So the enabling condition is implicitly true. Actions that are always enabled don't require an explicit enabling condition. But pop is only enabled when there is something on the stack. So pop enabled simply returns stack. That is, it's just testing whether the stack is empty or non-empty. So these enabling conditions are crucial to trace generation. Now, something else we do a lot in model-based testing is we do analyses of the models. So you need this for a number of reasons. So I'm going to explain it. Basically, and there's a program, the PyModel Analyzer, PMA, that does this in PyModel. And what the analyzer does is it generates a finite state machine from an infinite model program. And it does this by basically starting at the initial, basically it uses a process called exploration, which exhaustively executes the model program over some finite domain and then generates a finite state machine. So you start in the initial state, you pick some enabled actions and you get new states, you have more enabled actions and you execute those and get more states, and on and on. Well, of course, with an infinite program, this will expand to something infinite. So in order to make it stop, you finitize it. So typically what you do is you give it a finite domain of argument values and then perhaps put some finite limits on the state. But within those finite limits, the execution is exhaustive. And so as a result, you have this model that you have this structure that you can query for all kinds of properties. You can check liveness properties, that is, does something good happen? You can check safety properties, does anything bad happen? You can check whether certain scenarios are possible. That is there a path that executes a certain scenario within this? And of course, all those answers you get to those questions are conclusive, but only within those finite domains. But these generated finite state machines can be quite large. They can have hundreds or thousands of nodes and edges in them. So and the modeling, the framework uses these generated finite state machines internally for a number of operations. So this analysis capability is actually quite powerful. I mean, it really means that the analyzer is essentially a concrete state model checker, similar to model checkers like SPIN or SMV or something like that. Okay, there's also something called programmable strategies. So like when I generated that trace, typically due to non-determinism in the system, the test generator has a number of choices for the action it chooses for the next action in a trace. So the default, so you need what's called a strategy. A strategy is simply an algorithm for picking which of the enabled actions you actually put in the generated trace. So the default strategy in PyModel is just random choice among the enabled actions. So it's essentially you get random choice of the next action. You can program your own strategies. PyModel provides some. One is called action name coverage, where it basically just tries to choose action names that haven't been chosen yet. So if you use that with the stack example, you get alternating pushes and pops. Another strategy that's provided is state coverage, where the strategy is to always try to reach a state that you haven't reached yet. So if you use that with the stack, it'll just keep pushing new values on. Okay, how am I doing on time? Okay, I'm going to have to really speed through this next thing. But there's this whole issue with any automated testing technique. There's this whole issue of scenario control. So suddenly you have the problem with automated testing is not generating tests. You can generate infinite tests. The problem with automated testing is generally focusing the tests. And that problem in the testing world is called scenario control. So out of the infinite possible traces you could generate, you want to focus on particular scenarios that probe some particular issue of interest. So how do we do that? PyModel uses an operation called composition, which is a way of combining two or more models to get a new model called the product. So typically what you do is that the system as a whole is described by one of these Python model programs that has infinite behaviors. But then what you do is you write your own little scenario machine, which is a finite state machine that represents the scenarios you're interested in. And then by using this composition operation, you can essentially use the scenario as a filter on the contract model program. This composition has 101 uses. It's just a fascinating thing, and I'll just concentrate on it for scenario control in this presentation. So so here's how it works. Here's our finite state machine. I'm representing the program by its finite state machine. So there's the infinite stack program. Here's a scenario, and there's the product. The way composition works is it's basically a generalization of the intersection of finite automata, but so it basically has it's like parallel execution of both machines. But the composition can only proceed when an action is enabled in both machines. That's how you get this filtering effect. However, it also interleaves unshared actions, so you can actually build up systems compositionally and add behaviors this way too. Another thing you can do is you can use composition to validate a model program. That is, how do a model program's just a program, so it probably has bugs in it. So how do we test it? How do we validate it? Well, one way is by doing this exploration and checking properties and stuff, but the most basic way is to just go back to unit testing. But the way you unit test a model program is you write finite state machines that represent scenarios, that represent traces that you know a priori should be allowed or should be forbidden. Then you compose those with your model program, and the traces that are allowed will run to completion, and the traces that are not allowed won't reach the end of the trace. And so that's how you validate the model program. That's how you unit test a model program using composition. So that's an example of that. So here's how you use it in practice. For example, here's a program that has a whole lot of redundant startup and shutdown paths that are not interesting for the purposes of your present testing problem. You can write a finite state machine that just specifies one particular startup and shutdown sequence and compose that with that program. And what you get are tests which always take those paths through startup and shutdown, but can still traverse around many different paths in the interesting part of the behavior. So that's an example of how you use a scenario machine in composition in order to sort of focus, in order to do scenario control and focus on scenarios of interest. How much time? Okay, great. Pardon? Okay. Let's see, there's so much more. I think I'll just kind of wind it up quickly. Okay, in addition to writing this model program, you also have to write a thing called a test harness for each system under test, which basically is a piece of software that connects your model and the test runner and the test running machinery to a particular system. This is a big challenge, actually. The test harness can be a lot more work than the model itself. Let's see, we haven't talked about that already. Something that model-based testing supports is using, it sort of increases your idea of what testing consists of. For example, you can rig up a model-based testing system to use log files as tests. This is sort of called passive testing. What you do is just you define all the actions to be observable actions. And that means you can observe a log file just as if it were a live test. And the tester will treat it as a test case and will tell you if there's nonconformant behavior in the log. Another thing I think is that the analysis tools make possible a development style in which you can actually use these models not just for testing, you can use them as design documents or as specifications. And so this is, it makes possible a development style, I think, where the design and the testing are better integrated, because the design is actually something executable that you can actually generate the tests you actually use from. And furthermore, this model is expressed in the same programming language as the implementation. So you don't have to buy this system development ideology, but the tool actually supports it if you choose to do something like that. So I think I'll close there and take questions.